Welcome to the Explainer. I want you to take a second and just look down at the shirt you're wearing right now. We honestly rarely think about it, but you are literally draped in a marvel of engineering. Today, we're going on this incredible journey, tracing the thread all the way from the breathtaking cultural heritage of India right down to the microscopic, completely invisible world of molecular polymer science. Now, I know that sounds like a massive leap, right? But as you're going to see, they are intimately connected.
It's kind of fascinating when you really stop to think about it. On one hand, you have the gorgeous, intricate weave of a traditional textile, and then on the very same token, you have the strict geometric rules of chemistry. The whole core premise of our explainer today is that the stunning beauty of a woven tapestry and the hard, exact science of molecular bonds, they're actually bound by the exact same foundation. You simply cannot have the art without the architecture.
So, here is our roadmap for today. We'll kick things off with the tapestry of Indian heritage, followed by the science of a fiber and mapping the fiber taxonomy. Then we'll dive into origin versus engineering, explore the chemical crossover, and wrap it all up with mastery of the thread.
All right, let's jump right into Section 1, Tapestry of Indian Heritage, focusing on the art of weaving and embellishment.
When we step back and really admire the incredibly rich, diverse cultural artistry of India's textiles, what we are actually looking at is an absolute mastery of materials. Think about it. The artisans are entirely at the mercy of their physical ingredients. Every single Indian textile has these totally unique features that are driven 100% by its raw material, its dyeing process, the printing, and the specific weaving techniques used. It's this grand tapestry where the physical elements strictly dictate the final masterpiece.
Now we can basically organize this rich heritage into two distinct buckets. First up, we have the woven heritage. This includes structurally complex, almost architectural traditions. Think Banarasi brocades, Kanjivaram, and Baluchari silks, or those famously warm Kashmiri woolen shawls. In these, the design is built right into the actual structure of the fabric itself. Then, on the flip side, we have embellishments. This is where a base fabric is decorated after the fact. We're talking about the jaw-dropping needlework in Kanta, Sujani, or Fulkari, or the stunning mirror work you'll find in Kutch embroidery.
Moving on to Section 2, the science of a fiber and exploring the molecular blueprint.
So how exactly do we actually create the threads that make these beautiful fabrics possible? Look, it's so easy to glance at a Banarasi silk sari and think, wow, that's pure magic. But to understand the physical reality, we have to strip away that illusion of magic and zoom way, way down to the microscopic level. What physically allows these stunning threads to even exist? Well, it all comes down to something known as the 1:100 dimension rule. By definition, for something to be a textile fiber, it has to be a unit of matter that is usually at least 100 times longer than its thickness.
Just try to imagine that extreme length to thickness ratio for a second. This specific stretched out geometry isn't just some fun bit of trivia. It's the absolute, non-negotiable physical prerequisite that allows these tiny individual units of matter to be twisted, spun, and woven into continuous yarns. If the matter didn't naturally have this extreme ratio, the whole thing would just fall apart. It literally couldn't hold a spin.
But zooming in even closer, what actually makes up the fiber itself? It all comes down to polymers, the absolute basic foundational unit of all textile fibers, whether we're talking about the cotton in a Jamdani weave or the silk in a Kanjivaram, is the molecule. And these molecules link up to form long, repeating chains called polymers. This specific polymeric structure, this exact molecular blueprint, is what dictates the unique properties of every single fiber on Earth, no exceptions.
Okay, Section 3, Mapping the Fiber Taxonomy, where we categorize nature and science.
Think of the overarching map for all these microscopic building blocks. The whole taxonomy tree basically splits immediately into two massive primary branches, natural and man-made. From there, it gets a bit more complex. Natural fibers break down into cellulosic, protein, or mineral categories. Meanwhile, man-made fibers mirror some of those exact same natural categories, but they also introduce completely new human-invented ones, like pure synthetics and metallic fibers.
What's truly wild here is the stark night-and-day contrast in how these two main branches actually come into existence. On one side, we have natural fibers. These are literally harvested directly from the source. Plant origins like cotton and flax, animal proteins like silk and wool, or even naturally occurring minerals out of the earth. On the other side, we have man-made fibers. These do not exist anywhere in nature, they're entirely engineered. They are spawned from liquid polymers through a highly controlled mechanical spinning process. We are literally extruding them into existence. And because we have the power to engineer them, humanity has developed some truly incredible, high-performance fibers. We've got pure synthetics that are composed of completely synthesized polymers. Think polyester, nylon, acrylic. Then we've created man-made mineral fibers like glass and ceramic for heavy industrial use. And even metallic fibers using aluminium, silver, or tungsten. Let that sink in. We are literally spinning solid metal into thread.
Which brings us to Section 4, Origin versus Engineering, looking at how processing actually shapes properties. The difference in how we get these specific properties is, well, pretty massive. Natural fibers are extracted straight from biological resources. They're mechanically harvested, meaning they possess completely inherent properties. Cotton is breathable simply because nature built it that way. Man-made fibers, however, are extruded via mechanical tools called spinnerets. Imagine like a microscopic showerhead pushing out liquid polymer that then solidifies into a thread. Because we completely control that showerhead and the liquid inside it, we can modify the structural properties on the fly. We can literally engineer in flame resistance or microbe resistance before the thread even officially becomes a thread.
All right, Section 5, the chemical crossover. This is where we really start blurring the lines.
Get ready, because we're about to flip everything we just talked about on its head. I want you to think about this question for a second. Based on the taxonomy we just explored, does man-made always mean purely synthetic? It's a super common, totally natural assumption to think that if a fiber is engineered in a factory, it simply must be an artificial plastic, right?
Well, plot twist. The chemical compositions absolutely do not stick to that neat little natural versus man-made divide. Industry frequently engineers man-made fibers starting from completely natural polymers. For example, if you check your clothing tags right now, you've probably seen viscose rayon, modal, or tensile. These are completely man-made, extruded through those microscopic showerheads we talked about, but, and here's the kicker, they are obtained from natural wood pulp, which means they are fundamentally cellulosic chemistry. Similarly, we can create polylactic acid fiber using natural protein chemistry. So the origin might be 100% nature, but the execution is purely human engineering.
Finally, Section 6, Mastery of the Thread and the Perfect Alignment.
Which brings us to our big, grand takeaway for today. Whether a thread is harvested by hand from a sun-drenched field in India, sheared from a pashmina goat in the mountains, or extruded from a high-tech vat of synthesized liquid polymers, the breathtaking beauty of our entire textile heritage relies on the exact same foundation. It all comes down to the perfect alignment of molecules. Art and science aren't opposites here. They're just two sides of the very same thread.
So I'm going to leave you with this one final thought. We have spent centuries mastering the natural fibers provided to us by the earth, which has given us the spectacular cultural heritage we see today. But as we continue to unlock and engineer entirely new molecular blueprints, what is the next grand tapestry going to look like? What are the artisans of the future going to weave when their threads are limited only by the bounds of chemistry itself? Thank you so much for joining me on this explainer. Keep learning, keep exploring, and I'll catch you next time.